Okay, the first paper will be evaluation of epoxy nanocomposite for electrical insulation system by Ms. Zhao. And Ms. Zhao is from China. She got a BS and MS degree in material science from Tsinghua University, China, and PhD from material science and engineering department at the Rensselaer Polytechnic Institute, USA, 2007. And then she worked for IEEE Corporate Research Sweden since 2008 on electrical insulation material.
Thanks, William, for the introduction, and thank you, everybody, to come for my presentation. And my name is Zhao, and I'm from IEEE Corporate Research in Sweden. And the topic I have today is some evaluation of epoxy nanocomposite as insulation material. Okay. Electrical insulations, as we all know, in a lot of different electrical applications. But insulation material is very important, and no matter what type of application, like motors, switchgears, transformers, cable, insulator or capacitor, you name it. In general, the environment and the requirements for insulation materials, they experience heat and thermal cycling, like you turn the machine on, turn the machine off, and they operate at different temperature, different environment. And so this type of cycling introduces a lot of mechanical stresses to the system. And so it requires the insulation material to have very good heat dissipation and also good ductility and compatible thermal expansion coefficient as the conductive material around it, in it. And also the electrical insulation materials will experience high electric field, as we know. So it needs good breakdown strength, also low losses. And nowadays we have more and more new demands, like everybody wants a more compact design of the machine, of everything, which means to introduce more higher electrical field to the insulation system. So how to improve all the properties like mechanical, thermal, and electric properties of the insulation system is very important. And I'm only going to talk about epoxy today, because epoxy is one of the most used insulation material in all different applications. And right now, there are a lot of epoxy that has been filled with micro-sized fillers to improve their properties. For example, the thermal conductivity. But there are some small problems. There are some problems that microfillers, they are kind of defects themselves. That they can introduce voids and microcracks to the system, which will decrease the ductility of the epoxy. Epoxy is very brittle, we know, and if the ductility decreases, that is not very good for the long time life of the material. So we are thinking of using nanofillers instead of microfillers, because we know nanoparticles has much higher surface area compared to the micro-sized particles. And when you have an interface between nanoparticles and the matrix, the interface normally behaves differently than the particle and also different from the matrix. So we hope to use nanofillers to improve the ductility of the matrix and also increase the thermal conductivity and maintain the electrical property, of course. And we also hope the processing method will be compatible with the existing method. So these are some results from previous work where we had university collaboration between IEEE and Rensselaer Polytechnic Institute in Troy, New York, with Professor Linda Shedler. There we developed this alumina-filled epoxy nanocomposites and with surface-modified particles and without surface-modified particles. So in these two SEM pictures, you can see the blue one is the particle-filled epoxy without any surface modification on the particle, and the green ones are the treated particle-filled epoxy, and where you get a stronger interface between the particle and the matrix. And the surface modification we used with silane at the time. So the results, on the bottom, this two curve, the left one is a representative stress strain curve. The pink one is a neat polymer, and the blue one is non-treated, and the green one is a treated nanocomposite. And you can clearly see that the strain to break of the treated one, both of the nanocomposites improve the ductility, or you can say strain to break. This is a tensile ductility. And especially for the treated nanocomposite, it was about a 39% increase compared to the neat polymer. And we also did fatigue tests. The details are in the paper I mentioned on the bottom, but I just showed one picture, one curve here. That's the axis. The y-axis is the crack growth rate, and the x-axis is the applied stress intensity factor. So if you are not very familiar with fatigue test, and this is an easier way to understand it. If we draw this line and assume we apply the same stress concentration factor on all these three materials, and if you see the pink one is the neat polymer, and the other two are the nanocomposites, and the crack growth rate of the nanocomposite dropped significantly compared to the neat polymer. It's about 1 order of magnitude drop. That means by adding nanoparticles, you significantly reduce the crack growth rate at fatigue test. And the reason for that, in those papers, we had a very thorough discussion about what are the possible mechanisms of improving the mechanical properties of the nanocomposite. Here, for both non-treated and treated nanocomposite, for the non-treated, you have a weak interface between particle and matrix, and for the treated one, you have a more stronger interface. And in both cases, we see crack deflection and plastic void growth, but they look a little bit different. For the non-treated one, this blue one, from my CM picture, you can see the crack is actually quite flat. And then when the crack reaches the particle, where you have a very weak interface, it's just pull out the particle and form a hole, or go above the particle, then you can see the spherical particle. But when you have a much stronger interface, on the bottom picture here, in the blue, sorry, in the green one, when the crack is approaching to the particles, and since you have a stronger interface, then the crack will go around the particles and in between the matrix, and which will increase the overall crack length. That since it absorbs more energy during crack deflection. And another interesting mechanism we noticed was for the treated particle field nanocomposite, we saw plastic deformation around particles. That's something we've never seen on non-treated particle or the pure epoxy. You just have very straight forward cracks. And for the treated one, during the fatigue test, we noticed there are some plastic deformation. So all these results was done on a small scale samples, like here we had in the lab about 100 grams, and then we mix the sample and cure the sample and test them. And is that possible to upscale this material to a much larger quantity that for some applications in a real case? And we're still going to get good dispersion, and is the property is going to be the same? So this is about this paper. We were trying to upscale this material from lab scale to at least about 5 liters. And the epoxy system here we used was a very simple epoxy system. It's a bisphenol A plus bisphenol F liquid epoxy. And we used curing agent was amine catalyst. And particles we used is the same, alumina as the previous work, and the average particle size is about 45 nanometers. And the concentration was 10 pHr. pHr means per 100 gram resin. So it's about 3 volume percent or 9 weight percent. That's the optimized weight percent we got from the previous work, where you get the maximum improved in ductility. And so we were trying to look for commercially available compounding method to upscale this material. The first one, this DEIS 150 in this picture in the red, and it's the same machine that we used for the previous work, that you can make a small quantity. And then the principle of this machine is you put the sample in a cup, and in the this one?
Yes.
Thank you. Here. So you put the sample in a cup, and it rotates in one direction, and the main stage rotates in the opposite direction. And there is an angle between the cup and the main stage. So this kind of movement provides a very high shear stress to disperse the particles, and you don't need to use any propeller. So it's very clean and neat. And so we try to use the bigger size of this type of machine is DEIS 3000 that can mix up to 3 kilograms of material. And the principle is the same, so it's a high shear stress machine. And another one is this Ross machine, and the model is, it's also a high shear mixer, but the principle is different. In this tape, we have a rotor and a small rotor with a propeller on it. And then it rotates around the stator where you have holes, and provide this type of movement in your material that helps you to disperse particles. And the last one was customized commercial master batch, and we had the collaboration with, and the compounding method was unknown, but we got the master batch directly from the supplier with the particles dispersed in there. And the particles are the same, this aluminum. So how do we see if the results are the same as the small scale? So we did some basic property tests, including viscosity, plus transition temperature, and also we checked SEM to see particle dispersion. And we did also the tensile test, and AC breakdown strength, and dielectric response, and in the end, thermal conductivity to evaluate all this material. And the color in the future slides will be the same, so the blue one is always the dark blue one is always set into epoxy. If you compare the viscosity at 50 degrees, and all the nanocomposite have higher viscosity compared to the neat polymer, that is reasonable since we add particles in there, but it's not significant high that we cannot accept. The glass transition temperature here, we have more or less, we can say there's no significant change of the nanocomposite since we are not using a very high quantity. And here the dispersions, that's one of the key factors we are checking. So for the machine with this high shear without propeller, this DEIS machine, you can see that we get pretty good dispersion, and if you go to a very high magnification, you can see individual particles. We do have some aggregates around 1 or 2 microns. And the Ross machine with the propeller, the high shear mixer, that we do see very big aggregates actually. So there are aggregates between 5 to 6 micron and even 10 microns. So it was very difficult to break those aggregates of the particles. And this commercial master batch, and there was no aggregates at all. It was extremely good dispersion, and individual particles can be seen clearly. So, and how about the mechanical property? That was the one we checked before for the small scale. And in this representative stress strain curve, you can see this dark blue one is a neat polymer, and light blue is the Ross master batch. And all the other 3 are the DEIS machine and the master batch 1. And for all these 3, we got pretty good increase in strain to break, above 33% or 40% roughly. And So the conclusion we got here was very simple. The good dispersion is really important to get any improvement in your mechanical properties of the matrix. And so how about the other property, like electric property? Then we chose the best dispersed master batch, this master batch 1, same concentration to compare with neat polymer. And here we used this geometry. It's rounded plate with 24 dimples or half recesses. So we tested in oil. The top electrode is half spherical and bottom electrode is flat. And so on the bottom where you tested it, the thickness is about 0.1 to 0.2 millimeter. So this is a Weibull curve of these two materials. The red one is the neat resin and the black one is the master batch 1. The AC breakdown strength, alpha value, they are very similar. We cannot say that this one is better. We just say they are more or less the same. There is no significant improvement or decrease. But if you look at the beta value, where for the nanocomposite, it's significantly higher than the neat polymer, although both of them are not as high as in another literature reported, which indicates our method is not perfect, but you still see the trend that for the nanocomposite, the beta value is higher. That indicates we have less scatters in the data compared to the neat polymer. That was also in line with a lot of other literatures. When you add nanoparticles, you get less scatter in data. And then the dielectric response. These are a lot of curves, so you don't need to read all of them. We tested the material, the nanocomposite and the neat polymer at 3 different temperatures, and if you just look at the curve from far away, they look more or less the same. So we say there was no significant difference between the nanocomposite and the neat polymer for both the dielectric constant and the losses. But we noticed a very interesting thing here. At 90 degrees, the nanocomposite actually showed lower losses than the neat polymer. And it was not the same situation in room temperature. And that's something very interesting, but we don't understand yet. And also we checked the thermal conductivity. There was no surprise by adding 10 pHr particles. The thermal conductivity of the matrix increased linearly, and there was no nanometric. It was the same as the micron fillers, and it's more or less a rule of mixture increase of the thermal conductivity. So, the summary of my talk. We try to upscale this alumina filled nanocomposite, and we noticed that the homogeneous nanoparticle distribution is really critical to achieve any improvement in the properties of the nanocomposite. And the large scale, well distributed nanocomposite could be achieved by using a speed mixer or the master batch 1 that we don't know how they really did it. The glass transition temperature of all the formulas remains the same as the neat polymer, where the viscosity of the nanocomposite increased slightly. And we saw significantly improved tensile ductility for the master batch prepared by the speed mixer, and the master batch 1, that means we'll get good dispersion of the nanoparticles. We improve the mechanical properties. And also this master batch 1 exhibits similar dielectric breakdown strengths as the neat polymer, but significantly less scatter in the breakdown strength data. And last one is compared to the pure resin, the nanocomposite has a slightly increase in thermal conductivity, and there is no significant change in the dielectric response of the material. And thank you for your attention, and I would like to thank Professor Linda Schemmer from Rensselaer Polytechnic Institute, and also Dr. Tommaso Oletta, who was involved in the project before. Thank you.
Before you ask question, please introduce yourself. And any question?
Paul Gerskin from FMC Technologies. Have you done any investigation on the effect of the nanoparticle thermal expansion coefficient?
Yes, yes, we did. It was by adding particles to the thermal expansion coefficient dropped, also linearly. And we checked it was also very similar to the rule of mixture, similar to the thermal conductivity. So it's getting closer to the copper, but still significantly higher than copper. And there was no significant magic there, decrease.
Ravi Guru of Arizona State University. Two questions. One, how did you measure thermal conductivity?
Okay.
And the other one is, did you consider using a microfilm epoxy, or are you planning to do that as a comparative comparison?
For comparison, we are not doing any microfilm particles epoxy because there was a lot of literature actually for microfields. And in general, you can see the ductility of the material will drop. And regarding the thermal conductivity, we are using a hot disk equipment. It was from Sweden, and now it's kind of standardized, but it's different from the IEC or ASTM standard. It was, you use two sample blocks, and then you have a sensor in between. And by applying electric current, and it heats up the sample on both sides and then measure the thermal conductivity.
From the GE Global Research, when you show the breakdown strength of the on-field resin, the beta value is so low.
Yeah, it was extremely low.
So nobody will use that epoxy.
Yeah, that's right. So that's a reason that when we did the test, that sample geometry was developed by Professor Keith Nelson at RPI, and he did a lot of research on the techniques which we should use, and so we used that geometry. There was only one available. It's easier to cast at that time. But we noticed it's not a perfect geometry for epoxy. It's better for thermoplastic in that geometry. But so since epoxy is very brittle, there can be cracks during the AC breakdown strength test. So we noticed that it was not a perfect geometry, but we just tried to see if there's any trend.
And when we show the tangent delta values, you report the loss value. Which frequency is that loss value?
Sorry, I forgot to mention. In that table, it was 50 Hertz.
Thank you.
You're welcome.